Hello everyone, my name is Neha Kardam, and in this lecture we are going to learn about IC specifications and simple interfacing. So in the last lecture we did a first part of this chapter, and now in this lecture we are going to continue and cover these topics. We will be covering interfacing with switches, interfacing with LEDs, interfacing with buzzers, relays, motors, solenoids, and then interfacing with other solid state relay, which is optical isolator, and then current sourcing and sinking. So let's begin with interfacing with switches. So we are going to see switch to TTL interfaces. And you can see the circuit. This is a TTL inverter here connected to the power supply of 5 volts. This VCC is 5 volts. And then this is a resistance of 10 kilo ohm. And then on the left hand side, we have this switch connected to the ground. So at this particular case, when VCC is connected to the TTL inverter and the switch is open, then at that point the input is going to be high. So if the input is high, then the output is going to be low, because this is a TTL inverter. So if the output is 1, then if the input is 1, then the output is going to be 0. Now the purpose of this 10 kilo ohm, this is first of all called your pull-up resistor, and this has been added to make sure that the input to the TTL inverter goes high when the switch is open. Its purpose is to pull the input up to 5 volts. We know that 5 volts is for TTL, that much it can supply. So up to 5 volts when the input switch is open. So this circuit you see here is called your active low switch. This is called active low switches because the inputs goes low only when the switch is activated. So just imagine, if the input is low, then what will happen? Your output is going to be high. Okay, so let's see that. So input is connected. Now in this case, what will happen? Your directly 5 volts VCC is going to go to the ground. So this is the shortest path it is going to cover. And if that's the case, then here you will have low input or zero input. If zero input is there, then at the output you are going to have 1 or high. So that's why you have this this case which is called your active low switch. Okay, so and in this particular case we have used pull-up resistor. Now let's see another example. Now in this particular case, you have TTL inverter connected to this 330 ohm resistor, and this resistor is called your pull down resistance. So, and then on the left hand side you see a switch which is connected to the 5 volts supply. Previously you saw that it was connected to the ground, but here it is connected to the supply, and the resistance, pull-up resistance, is connected to the supply, and here this pull down resistance is connected to the ground. So let's consider two cases. The first case is when the switch is open. So this is the first case. When the switch is open, then what will happen? So when the switch is open, then no 5 volts will go into this into this node because the switch is open. So what will happen? This will be at a low potential. Okay, so the input to the TTL inverter is going to be at a low potential. So if it is low, then we are going to have inverted output, which means we are going to get high, and that's why you see here high. And then second case would be when the switch is closed. So let's see what will happen. When the switch is closed, then you are going to get high input to the TTL, right? So if your input is high, then your output is going to be inverted, and that's why you got low. So this type of circuit, if you see, this is called your active high circuit, and this switch is called your active high input switch. And this resistor is called your pull down resistance because it pulls the it pulls the input to the ground level or at a low potential. Now here the value of this pull down resistance is relatively low because the input current required by a standard TTL gate, it may be as high as 1.6 milliamps. And then you see these are the two cases. One is for pull up resistor and second is for pull down resistor, and this is your active low and this is your active high case. So the same you can apply with CMOS. Like when you interface the switch, you connect with the CMOS. So instead of this TTL, you can use the CMOS. So let's see, switch to CMOS interface. So here we have represented in the same way CMOS, but here we are using different resistor. You can see here we are using 100 kilo ohm resistor because the parameters for the CMOS is different compared to the TTL. It is high power. So based on that, we have used 100 kilo ohm as a pull up resistor, and pull down resistance is around 100 kilo ohm. Now quiz. So the component labeled A in the interfacing circuit is called a pull up or pull down resistor and is holding the input to the inverter high. So this type of this is called your pull up resistor because it is pulling the high voltage. So it's going to be pull up. And then we have a component label B in the interface circuit is pull up or pull down. So this is pretty simple. This is a pull down resistance pulled up to the ground. And then you have the output at C is currently low or high. So what do you think? So right now, based on this particular circuit, we know that the input is connected to the ground, so this is going to be low, and I'm assuming that this is our TTL inverter. So it's written also here, the pull down resistor is holding the inverter's input low. So in this case, the inverter's input is low, then we are going to get the high output. So that's why you have high. Now next we have switch debouncing. So let's read here. It says mechanical switches that serve as inputs for some digital circuits like counters may need switch debouncing. A low to high switch transition can result in high, low, high bounces. So what happens if you use like a push button or a toggle switch, and if you press it, then you know that the two metal parts, they come into contact to short the supply, but they don't connect instantly. And what happened, the metal parts, they connect and disconnect several times before the actual stable connection is established. And the same thing has happened when you release the button. So this phenomena basically results in the false triggering or multiple triggering, as if like the button is pressed multiple times. So in this situation, so if you want to input a manual switch signal into a digital circuit, then you will need to debounce the signal, as a signal press doesn't appear like multiple presses. Okay, so for that we uses debouncing latches or debouncing switches. Okay, so you can see in this particular demonstration that this is some digital circuit, and this is the mechanical switch, you can say, connected to the high and low, and this is further connected to a debouncing latch. Okay, and then at the output you will get the debounced signal. Okay, so let's see, when it is low, then you get the low signal, and when the mechanical switch is on the high, then you get the high signal, and then again from low, then you will get the low signal. So you notice that there is no switch bounce in this particular case. They are only highs and lows, but there is no signal is like going in between like this, like bouncing. So, and this happened because you use the debouncing latching. So you might be thinking, what's there inside this debouncing latch? So there are many different ways you can use the debouncing switch, or you can create your own. So with with the different approaches, the basic one is to use the capacitor to filter out any quick changes in the switch signal. And you can also use RS flip-flop, which uses cross-coupled NAND gates that will make up a debouncing switch. And you can also use debouncing switch with 555 timers. So there are many different circuits which are available and can be used as a debouncing latch. Now let's see this quiz. It says the output waveform at A going low high is referred to as a analog or digital. So this type of signal is your digital, which is a discrete signal. So you have only two inputs, high and low. The block label B, so this is your B block, is a switch latch. What type of switch it is? It is a debouncing switch. So that's why you have debouncing here. And then you have low high output of the SPDT switch. SPDT is single phase double throw switch. On the left is debounce. So this SPDT it is talking about is debounced by the electronic device B. Is this condition true or false? So this is true because this mechanical switch is connected to the debouncing circuit, so the signal is going to be debounced. So that's why you have the answer is true. Now next we have interfacing the TTL or CMOS to LED. So you see here this is the TTL inverter, and or you can use CMOS here. So in this particular case, the CMOS or the TTL is connected to the 33 kilo ohm resistor, and then further to the transistor, and then there is a LED connected here, and then further 150 ohm resistor is connected to the supply, and then the emitter side of the transistor is grounded. So this is the case one when the transistor is off, and when transistor is off when the base is low, and the output of the CMOS or the TTL is low when the input is high. So when the input is high, then because it is a TTL inverter, so if you have high here, then this is going to be output, at the output is going to be low. So if the output is low, your transistor is going to be off, and if the transistor is off, then the LED will not get enough power to turn it on. Now let's see the second case. If you give the low signal to the TTL, then what will happen at the output? You will have high, so you have high voltage, and then that signal will go to the transistor and it will energize the transistor. Once the transistor is on, then what will happen? It will turn on the LED. Okay, so in this case you can see the LED is turned on and the supply goes like this to the transistor, turning it on. So you can see here either TTL or CMOS ICs can drive an LED using a transistor. Left arrow key on keyboard to erase and see action again. So you can you already saw that previously it was high and then it was low, and in that situation transistor was off, and in the second case when you give the low input, then your transistor is on and LED is turned on. Now next is the quiz. If point A goes high, so this is the A point, goes high, point B will be low, and the transistor will be turned off, causing the LED to turn on or turn off. So if the transistor is off, then LED will be turned off. Okay, and then we have, if the point B goes high, if this is high, and the transistor will turn on, causing the LED to turn on or turn off, so it will be turn on. And then the inverter can be from either the TTL or CMOS family of ICs and can be able to drive the indicator LED. So is it a true condition or a false? So it is true because we learned that this TTL or CMOS can be used in this circuit. So if that's the case, then we can turn on or turn off the LED. So this is true. Now let's see interfacing with buzzers, relays, motors and solenoids. So the So let's see. First is a piezo buzzer, uh, a signaling device drawing less current than older buzzers and bells. So this is a modern buzzer in which you can it can create a noise, or it's like a bell, but it is not like a traditional buzzer. Uh, and then we have AC or DC motors, which produces continuous rotary motion. So motor voltages and current not compatible with logic circuits. So when you use this, the sometimes what happened, the drive capabilities or these voltage or current parameters, they are not compatible with the circuit, so you have to use some auxiliary circuit to connect them together or interface them, and that's what we are going to see next. And then you have a solenoid. It's a device that can put linear motion, so you must have worked with solenoid in your lab experiments. And then you have the relay, a device to isolate logic device from high voltage or current circuits. So relays, they are used in circuits to isolate the voltage or current or high current. So that was the relay. And then we have opto-isolator, a device to isolate logic device from high voltage or current circuit. So actually these two both are relays. Opto-isolator is also a type of relay. This is a solid state type of relay, which are like more modern type of relay. And so we're going to see all of these and their interfacing circuit next. Now our first is interfacing with a piezo buzzer. So you see, a piezo buzzer is our output, which is connected to this logic circuit. And this piezo buzzer, it is a modern signaling device which draws much less current than old buzzers or bells. And here you see a standard TTL is used, or you can use FACT. FACT is the CMOS. And if we see the current carrying capability of these two, then the TTL output can sync up to 16 milliamp, while the FACT or the CMOS output has 24 milliamp of driving current. So here the piezo buzzer, you see, it can draw between 3 to 5 milliamps when the sound is on. And you notice the polarity of the piezo buzzers. You see, this is negative and this is positive. And there's a diode connected across the buzzer. So this diode is suppressed. It is used to suppress any transient voltages that may be induced in the system by the buzzer. So now let's see how it works. If your input is low, then the output is going to be high because this is a inverter. And if it is high, then the transistor will be on and the buzzer will sound. Okay. And if the input is high, then the output goes low. Transistor will be off, turning off the buzzer. And here, in this case, the diode protects against if there is any transient voltages there that will bypass through this diode. Now, quick quiz, when the input to the inverter goes low, the buzzer goes what? So if the input is low, then this is high, this will be turned on, then the buzzer will be on, which means it is going to sound. Next we have when the input to the inverter goes high, the input to the transistor goes low, which turns on or off both the transistor and the buzzer. So in that case, it is going to turn off the transistor and the buzzer. Now next is isolation logic to high voltage and current. So we have electromechanical relays. They are the older method of isolation. Relays are expensive, heavy, and produce noise. So these electromagnetic relays, they are those relays which operate on the principle of electromagnetic attraction, and it is a type of magnetic switch which uses the magnet for creating a magnetic field. The magnetic field then uses for opening and closing the switch and for performing the mechanical operation. And then we have this opto-isolator, or it is also called optocoupler. It is lightweight and it is alternative to electromagnetic relay when interfacing with logic circuit. So these are more modern type. So if you see the traditional type relays, they have like several mechanical failure modes associated with moving parts. So these the solid state relays, and this is one of the solid state relay which offer several advantages in performance and in terms of design also. For example, they include a low power consumption, low leakage current, stable they have stable on resistance, they have high reliability, they have extremely long life, and their size is also is also small. They have the fast switching speed because they use the digital logic circuit. They have high vibration and shock resistance, and they do not have switching noise from contact bouncing, which is very much there present in the electromechanical relays. And then we have solid state relay. These are more, this is also solid state relay, but here we have like mentioned like heavy duty version of the opto isolator. And the important feature of this solid state relay is that they are optically isolated, which means that the relays they use an LED or light emitting diode on their input side, or MOSFETs on their output side, and an array of photosensors isolating the two of them. So let's begin with interfacing using our relay. So here you see this is our electromechanical relay which is connected here. You see this is a coil is there, and then and then this switch is connected, which is forming a relay. So every time the magnetic field is changed here, the switch will respond accordingly. So let's see what will happen. And then this whole is the output. You see, you have this electromechanical relay, and then you have the diode is connected to avoid any transient voltage, and then you have this output DC motor is connected. So you can see here, if the DC motor is connected to this terminal, then what will happen, the DC motor will be off, and if the switch is connected to this position, then it will make a closed loop, which means the DC motor will be supplied by 12 volts. It will turn on the 12 volts. The 12 volts will turn on the DC motor. So let's see. And then this is the transistor, and this you already know, TTL or CMOS is used. So normally open relay contacts, and you have low voltage of 5 volts side of circuit, and this is your high voltage 12 volts side of circuit. So now we are going to see the different cases when different inputs are provided here. So when you have like high input here, then what will happen, you are going to have low output. So if you have the low output, then transistor will be off. In that case, there will be no movement here, so coil will not be energized. So normally open contact will remain open. So this is a normally open contact, so this will remain open, and in that case DC motor will not run. And when the input is low, then the output will be high, which will turn on the transistor, and in that situation some magnetic field will be created, and due to which this switch will connect to the another contact, this, and close the contact, and then 12 volts will be supplied to the DC motor. So DC motor will turn in this anti-clockwise direction. Now, quick quiz: if the input to the inverter is low, the transistor will turn on, the relay coil will be energized. Is it true and false? This is true. If the input to the inverter is low, the transistor will turn on, the relay coil will be energized, the NO relay contacts close, and the motor will run. So is it true or false? This is also true. And then third one, if the input to the inverter is high, the DC motor will run or not. So if the input is high, this is going to be low. So if it is low, this will not be energized, which means the it will not make the switch will not snap to this position. So it is going to be off in that particular case. Now next we have optical isolation. So these optical or opto isolator, they are very useful device, and they are alternative to electromechanical relay or electromagnetic relay, and they are used with digital circuits. And one close relative of opto isolator is the solid state relay. So you can see here, this is our optical isolation relay used, connected to this bulb, and then to the ground, and then here transistor is there, and then this is resistor, and then you have like TTL or CMOS is connected here. So this is a very similar circuit to the previous one, only the output has changed. So let's see what will happen. So if you have like a signal going in, a high signal is going, then what will happen? It will turn on the transistor, and then this will be energized, and then that will turn on the bulb. So I'll just go back to the previous. And if you have like a low signal, then what will happen? It will be turned off, and this will also be turned off, this bulb. Interfacing using opto isolator. This is another circuit you see. This is the opto isolator, which is connected to this piezo buzzer. So here are different outputs. We have this hole is the piezo isolator, and then it is connected to a piezo buzzer. The other side is connected to the ground. So let's see what will happen if we give the input here. So if the input is low, then the output is going to be high here, and if it is high, then this pin pin 2, which you see here, is going to be high. So in this case, if this is high, the LED you see here, this is going to be turned off, because you know that this is the cathode side, this is the so you know that this is the negative side, this is the positive side, anode side, and this has to have like a low voltage in order to turn on. Okay, but if it is high voltage, then this is not going to turn on. So this hole is turned off, and in that case you will have no sound. But if you have like a high input going in, then you will have like low output coming out. So at pin 2 it will be low, so it will forward bias this LED, and this will be turned on. So this optical oscillator will be turned on, and then what will happen? Your buzzer will be turned on. It will energize this, and then you will hear some sound. So that was the interfacing of opto isolator with the piezo buzzer. So quick quiz: if the input to the inverter is high, the LED inside the opto isolator light, the transistor turns on, and the buzzer sounds off, and the buzzer is silent. So in this case, it's going to be on, and the buzzer will be sound. Opto isolator IC isolates the low voltage input from the high voltage 2 volts output. So is it true or false? So again, let's read it again. The opto isolator isolates the 5 voltage, so 5 volts input from the higher voltage 12 volts. So yeah, it does that, because that's the position when it is at 4. It isolates 12 volts when there is no sound. So this is a true statement. And then we have there is a low resistance electrical connection between the input logic circuit and the output buzzer circuit because of the opto isolator IC. So you have so there is a low resistance electrical connection between the input logic circuit, so input logic circuit, and the buzzer circuit. There is no as such low resistance electrical connection is there, so this is going to be false. Now next we have IC's sourcing and sinking current. So these are the two circuits which are given. This is the TTL AND gate, and you see that the output of the TTL AND gate is connected to an LED, and then further to the resistors and to the ground. And in another circuit, this is the TTL NAND gate. You see this NOT, and then the output of this is connected to the LED. So the cathode side is connected to the output of the TTL, and then the positive side is connected to the supply of 5 volts, whereas here the negative side was connected to the ground. So in this case, if you see, if you have like high in AND gate, if you remember, if you have like 1-1 logic, then the output was also 1. So in this particular case, when you have like high input, then output is going to be high, so which means the 5 volts will directly go into the LED, turning it on, and further going into the ground. So this type of circuit is called your active high, and this is called IC sourcing. So active high output, and this type of circuit is your sourcing, because the load, this is, let's say this is our load, and load is getting the power from the source, so that is why it is called your source. So that is why it is called sourcing, or you are getting the source current. The load is getting the source current. And in the second case, if you see, so this is the TTL NAND gate, and you have like two inputs high, and if these two are high, then in the NAND gate the output is going to be low. So if the output is low, this will be low. So this is cathode and this is anode side, so this will again turn on the LED, and the power supply goes from here and then back to the TTL and then to the ground. So here this is called your sinking, and this current which flows from the power supply to the ground is called your sinking current. And so above was an example of the IC sourcing current to drive the output LED. Conventional current flow is going to be like this. So notice the IC has active high output. So in this case it has active high output, and in this case it is active low. So it is activated when it is low here, then your output is activated, and it is activated when your output is high. So active low output, and then it says an example of the IC sinking current to drive the output LED. Convention current flow has been shown from here to here. So notice the IC has active low output. So this was the last topic of this chapter. I hope you learned something today. So thank you so much for watching the lecture.